Okay. So we are doing problem 16.125 of the suggested homework problems. So what this says is the 3-pound uniform rod BD is connected to crank AB. A couple, which is not shown, is applied to AB, causing it to rotate with an angular velocity of 12 radians per second counterclockwise and with an angular acceleration of 80 radians per second squared clockwise. So neglecting the friction and the weight of the collar D, it asks us to find the reaction forces at D. So before I start, I'm just setting up my coordinate system. So I'm saying this is positive I, this is positive J, and this is positive K. So just going to state my givens. So we know that the weight, which is W, not omega, so that's how I'm going to have to write weight. So we know the weight of collar BD is equal to 3 pounds. We know that the angular acceleration, so that also looks like a W, but it's the Greek letter omega. So we know the angular acceleration of AB, the smaller crank, this one right here, we know that is given as 12 in the K, and that's positive in the K. And then we are also given that the angular acceleration of crank AB is 80 radians per second, but counterclockwise, or clockwise rather. And because of how I define this, from the givens and how I define my coordinate system, that is going to be negative 80 in the K. So here's all our givens. I'm gonna try to keep like this side up the entire time, and then also like the first base equation I start with, just so everything ties in easier. So this is everything we know, and we are asked to find the reaction forces at D. So a lot of ways that people approach this is they just start solving things, right? I mean, like you could apply all the equations that we've been using for the past month, you know, just like starting on crank AB and just finding the acceleration of B and then getting all the position vectors and all the velocities and stuff like that. And a lot of people would start it that way. But I've done this a lot before. I always just start from the most basic thing of what it's asking me to do. So find the reaction forces at D. So I'm going to draw a free body diagram, which equals the kinetic diagram, right? Because I'm trying to find forces at D. So I'm going to look at BD specifically because the crank AB doesn't mean anything in terms of trying to find the reaction forces at D, at least at this moment. So here is the free body diagram or kinetic diagram. I forget the terminology, but whatever. So BD, so here's D, B. So So this is the reaction force at B in the x direction, and this is the reaction force at B in the y direction. And I'm assuming they're both positive at this point, because in my opinion, it's always better to assume positive. So then here's the reaction forces at D, which I'm also assuming are positive. So D in the x and D in the y direction. And then there's one more thing. They tell us that crank BD has a weight. So we know at the center of mass, which I'm going to call G, we know there is a 3 pounds force right here. So we know that this whole thing right here equals, force equals mass times acceleration. So we have at this same point G, we have mass times acceleration of G in the y direction, assuming positive, and then mass times acceleration of G in the x direction. So this is what we're trying to solve here. We are trying to solve for dx and dy, and yeah. So so you might be tempted to do the sum of the forces first, and you definitely can do that, but I'm going to do the sum of the moments first, and there's a very specific reason for why I do that first. If I sum the moment about b, then bx and by have no effect on the sum of the moment. Does everyone understand that? That's important. Bx and by do not cause a moment around b. Everyone gets that? Because because a moment is force times perpendicular distance, and the perpendicular distance of by to b is 0, and also bx to b is 0 in terms of the perpendicular distance. So if I sum the moments around b, all I'm going to get is this weight times its distance, and then these things times its distance, and that's what I want, because I'm trying to solve for these reaction forces. So, doing that, sum of the moment about b is equal to the moment of inertia of rod BD times the angular acceleration of BD, and then it's also plus mass times acceleration of G in the y direction times the perpendicular distance. 2b, so G, 2b with respect to G. Any questions here? So this is like the part of the equation that's known, and then you have to go through and do this part. This is telling you an operation to do. It's telling you to sum the moment about b. So yeah, when we do that, let's see. So bx and by cause no moment when we're summing it about b. The weight does cause a moment. So what moment does it cause? About b, it would be, if this force is going this way, it would make that system rotate like that. So what is that? Rotates this way, so then my thumb is pointing that way, so negative. Everyone sees what I did there? Like the right-hand rule? So this force would cause this rod to spin that way. So when I do that with my hand, spin that way, my thumb is pointing backwards, so negative. So we have the weight of BD, and it's a negative. So then we need to find the perpendicular distance between there. So I just know from where this is, like if I draw this, this is the mass center, and it's just going to be halfway up these things. So like this is 4, like that. So 4 inches. And I'm going to put it in terms of feet too. So 4, but over 12, just to convert it to feet, right? So that's the first term. Then we need to find the moment that dx and dy causes. So in the exact same manner, let's see, dx would cause this type of motion. It would make it go that way. My thumb's pointing this way, positive. So it would be dx times the distance. So this one's given to us directly right here. So actually, not exactly directly, but actually is. Yeah, definitely. 6, 12. So yeah, 6 inches, and then the conversion to feet again. Then one more. So dy, what kind of moment is it causing? Positive. So plus dy. Then the distance is given directly, because if we're looking right here, the perpendicular distance to B is given 8 inches. So times 8 over 12. Okay. So then that's this part. This is the sum of the moment about B. And then I have this entire part right here, which I'm running out of space, but this equals I alpha BD plus mass times acceleration g of the y. And the perpendicular distance from right here to B is 4. Yes, 4. Yeah, for the y one it's 4. And that is positive moment. Mass times acceleration g in the x, 3 over 12. Yes, 3 over 12. Okay. Does everyone see this? Any questions here? What's up?
Yeah, can you just explain what dBg is?
Yeah. So it's the perpendicular distance from B to G. So if this is G and this is the perpendicular distance that we're looking at here.
Oh, okay.
And then like for this one, the perpendicular distance would be like this way. So do you see how those numbers are 4 inches and then I convert it to feet? That makes sense?
I just didn't see the G, like where it was G on the.
Oh, okay. Okay, cool.
Thanks.
So, gonna write out this entire thing. So that equation is just everything written nicer. So any questions here? So this is the point where I'm going to go through each one and say, what do I know? So this is the base equation that I'm going to be referencing the entire time. And more specifically, I'm going to let this equation guide me on what my steps are throughout this entire process. So right there, we're given the weight of VD, so I have that variable. dx, that's what I'm trying to solve for, so that's good. That's good that this showed up, and it's okay not to know it. So is dy. I'm told that find the reaction force of D, so I need to find that. The moment, or the, what is I again? I forget the word, but moment of inertia? Yeah, moment of inertia. I don't have it, but it's a constant, so it's a constant just for a rod. I'm not going to spend much time on it. It's just an equation that you're going to be given, like on a formula sheet, so you don't find it, you just compute it. Then there is the angular acceleration of rod BD. We do not have that, so we'll need to get that. We have the mass, because mass and weight are related, and we're told that the weight is right there. Acceleration of g in the y direction. We don't have that, so that's bad. And then acceleration of g in the x direction. We don't have that. So 3 unknowns here. 3 unknowns that aren't supposed to be unknown, and then 2 unknowns that are okay because that's what we're trying to solve for. So really 5 unknowns at this point. But we can start simplifying things. So first one, we are neglecting friction in the weight of the collar. So if we're looking at this thing right here, there's no friction and there's no weight. So there's nothing going on at D. at least in the y direction, that is, right? So this term becomes 0, that whole thing. So like this can go away now. And now we know the reaction forces at D are only in the x direction. So this side of the equation's okay because we're trying to solve for this. We got to look at all the things on this side and try to find them. So first one here that I'm going to do is this, the angular acceleration of rod BD. So is everyone cool if I erase like this part? Trying to find angular acceleration of this rod right here. So how are we going to do that? Well, I know that at AB, at crank AB, I'm given a bunch of stuff, especially in terms of its angular velocity and its angular acceleration. And I know from experience that in order to get this, I'm going to need the acceleration of B at some point. So instead of starting with crank BD, I'm going to look at crank AB because I know I can find a lot of stuff which is going to help me with this. So if I look at this crank AB, we have the this is alpha AB, and this is omega, so the angular velocity and acceleration, which are given. So then we're also given that this is 3 inches. So there's a lot of hints on why looking at crank AB would be a really good idea. We know so much about it. So here we go, base equation. Acceleration of B equals the acceleration of A plus alpha AB crossed with RB with respect to A minus AB squared and one more thing. Acceleration of A is 0 because it's a pin, right? It's a pin down. So it's pretty clear from here that with all this information, we can definitely get acceleration of B. So specifically, alpha AB, we're given that in the problem. The position vector, that's easy to find. So yes, we have that. The angular velocity, we're also given that. So we're literally given everything to find this. So then at that point, it is just the actual computation of it. So what that is, acceleration of B equals negative 80 in the k direction crossed with the position vector. So 2b from A, 2b from A, 2b from A, negative 312, okay. So do that cross product, and then what is this? This is given as 12 squared times negative 3 over 12. So this is how I compute the cross product. So J cross, or K cross J, K cross J is negative. So there's 3 negatives here, so this term is going to end up being negative in the I direction. So we have 80 times 3 over 12, and it's going to be negative in the I direction. So 2 negatives here, this is going to be positive. Whatever this computes out to, 36, yeah. 36, and that, because this is in the J direction. So this number right here, this computes to 20. So and it's negative. So there we go. We have the acceleration of B. And that was really easy to get because we had so much known about AB in the first place. So, cool. So, while I'm looking at this, I'm also just going to find the velocity. Just because normally I wouldn't do this because I don't just like solve things without a motivation for it, but I have everything here. So like I literally have all the variables. So it's a very simple computation, and I figured why not. Okay, so we have the acceleration of B and the velocity of B, which we are then going to use when we're going to look at crank BD to eventually find alpha BD, right? So, any questions? Good if I erase this part? Yeah. So, now looking at crank BD. And now we know a lot about B, that is, we know its velocity and its acceleration. So we're going to use that information to find the angular acceleration of the rod entirely. So, base equation, acceleration of D equals the acceleration of B plus alpha BD crossed with R, B with respect, D with respect to B, minus BD, R, D with respect to B. That's squared. All right, so we don't know the acceleration of AD. We do know the acceleration of B. We just found that. Alpha BD, that's what I'm trying to solve for in the first place over here from our major base equation. So it's okay not to know this. I don't know it, but that's okay because I'm trying to find it. So it's actually good that it shows up, right? So position vector, I can get that. That position vector I can get. Angular velocity of BD, I do not have that, so that's bad that I don't know that either. So, next step, I need WBD, right? So, what I'm going to do is apply the instantaneous center of rotation stuff. So if we have, assuming velocity of D is this way and velocity of B, actually I know the velocity of B is in that direction, and D can only move up and down, right? So that's how I know these are right. Perpendicular to these, right here. This is the ICR, the instantaneous center of rotation. So applying the stuff that I lectured about like 2 or 3 weeks ago, we can, find, I'm going to find the angular velocity of BD, knowing, because I know the instantaneous center of rotation right here, this velocity is 0. So specifically, VB equals the velocity of the ICR, which is always 0, plus base equation is BD crossed with R, E with respect to the ICR. That's 0. I know this, I found that earlier. This is what I'm trying to find in the first place. And I can definitely get that if it's just a position vector. Cool. So, what this is, 3 in the I, that's the velocity of B, found it earlier, is equal to omega BD in the K crossed with, okay, 2B from the ICR. It's positive. 6/12 and the J. Everyone see where I'm getting that number from? The instantaneous center of rotation is like right at this point, and it's 6 inches. Right, so then converting that to feet, just dividing it by 12. So then one equation, one unknown. After I do this cross product, you can find this, which is equal to -6 in the K direction. -6. So, coming back here, now I know that, right? So, then I'm going to use that to find alpha BD, which I was motivated to do in the first place because I'm trying to find this unknown back in the major equation, the one I started with. So, what am I going to do at this point? So, is everyone cool if I erase this?
Just a question. Since we went from B to ICR, does it have to be -6 or is it just +6?
So the position vector is positive. It's how this notation is, like when you say A, B, it's in words 2A from B,
Okay.
right? So this means 2B from the ICR. That means I'm going this way.
Gotcha.
2B from the ICR. I define positive J, so that's why that's that.
But the
Yep. Right. So acceleration of d in the I plus acceleration of d in the j. Also, shorthand is just acceleration of d, but I'm just highlighting that the acceleration of d in the I direction is 0. So I'm going to use that fact to solve this. Because at first, when I write this equation, it might not look like it's ready to be solved, but it actually can be. Okay, so this is the equation that defines BD. I've written this like 3 times at this point, but we just solved for that. I can definitely get that. I can definitely get that position vector. This is what I'm trying to find in the first place, and I have the acceleration of B actually. So I'm going to split this into I and J components, and that's how I'm going to solve for this. So, acceleration of d in the j is equal to the acceleration of b that we found earlier was -20 in the I plus 36 in the j. So that's the acceleration of b part. Then this is alpha bd in the k crossed with, I'm just going to get the position vector. That's 8/12 in the I minus 6/12 in the j. So that's that part. And then that is minus, we just found angular acceleration of BD, and that was -6. So that's -6 squared times the same number right here. So before I split, I'm gonna just do all the computation. So that's K cross I is J. So that's in the J, and then K cross J is negative I. 6/12 alpha BD in the I direction. Computing this thing right here, double parentheses. What does that come out to? That comes out to Is there any questions with the computation there? So the really helpful thing about this is that the acceleration of d in the I direction is 0. So specifically, I see alpha BD in the I direction, and then the rest I see for the I are constants. So that's how I know when I split this in I and j, I'm going to be able to solve for it. Specifically, looking in the I direction only, it's 0 equals negative 20 in the I right here, then plus 6/12 alpha BD, right? And then minus 24 in the I. These are all just positives at this point, or not positives, constants, right? So solving for this, you get 44 I equals 6/12 alpha BD. Alpha BD equals what, 88? Yeah, 88, and that's positive, so 88 in the K direction. Any questions?
I have a question. When you did the R from D to B, right, should that I component be negative because you're going in the left direction? The negative direction from D to B?
You're right, but okay, you are right, but I actually wrote it wrong. This
Okay.
is D with respect to B.
Oh, okay.
Yeah.
Okay.
So yes, you are right.
Okay.
But, so I just like did a typo here wrong, but now this number is right, right? That makes sense?
Yeah.
Okay. Any questions? Okay. Cool. So, back to our main equation. We have that now. Still two other things to do. Acceleration of g in the y and in the x direction. But we're getting there, right? So, everyone good if I erase this? So now I need acceleration of g in x and y direction from that. So how am I going to get that? Here's the crank. G, D, B. I know the acceleration of B, and yeah, I'm going to use that fact to solve things because now I know the angular acceleration of this rod and I know the angular velocity from all the previous steps I just did. So now I have a ton of information and I can write now this base equation. Acceleration of g equals the acceleration of b plus alpha bd. We just found that. Crossed with position vector g with respect to b. So acceleration of g, I don't know, but that's okay because that's what I'm trying to find right here, those two components. Acceleration of b, I found that a while ago. Alpha bd, just got that. Angular acceleration of bd, got that in the step before getting this. Then the position vectors I can definitely get. So very clear I can get acceleration of g in all directions pretty easily from this. So from the lengthy but thorough process I did getting alpha bd, getting this last part is going to be very, very simple, right? So I really stress, take your time and look at the variables you're doing, make sure you don't miss any steps. Because at this point, this problem is going to be very easy to solve. I don't really have to do much other than finding the position vectors, but that's all just given. It's really just like looking at it and seeing where things are, right? So, all right. Acceleration of g in the I plus acceleration of g in the j, which is analogous to the x and y, right? So acceleration of b, that again is 20 in the I plus 36 in the j. Then alpha bd was 88 positive in the k direction. 2g from b, 2g, that is negative or positive 4 in the I. Then what? Negative 3? Yeah. Or rather, no. Yeah, positive in the I, negative in the j. Right, so that was 6 squared times 4 over 12 in the I, 3 over 12 in the j. All right, so have a good one. All just computation at this point. There's literally no unknowns. We're kind of running out of time, so I've done the cross product like a bunch of times at this point, but everyone just understands that this is just computation at this point, like literally just calculators, right? So you get acceleration in the g direction is equal to negative 10 in the I plus 74.33 in the j. Just numbers on this side. We can get this side explicitly. When you put that all in, this is what you'll get. Any questions? Good? Awesome. All right, so back to the first equation. Right. Acceleration of g in the y direction, which is analogous to j. Just got that, and just got the one in the I direction, x direction. So that's known, that's known, that's known. That's what I'm trying to find. The last step is the moment of inertia. And like I said, this is like for a rod, the moment of inertia is just equal to, and again, this is going to be something that is just like on an equation sheet, so like, it's not a big deal here. So, yeah, that's the length of the rod. This is the length of the rod, 10 over 12, from, you have, right, 8 squared plus 6 squared, square root. And then if this is over 12, that's over 12. That's how you get that. It's just the hypotenuse, the Pythagorean theorem, right? So, like this is constant stuff, then this is length squared. I did the computation already, it's 10 over 12, but it's literally just the hypotenuse of that triangle form right there, right? So, doing that, we get I is equal to 0.17361 divided by the gravity constant. I didn't do the computation for some reason, I was doing it, but All right, so I can finally go back to our first equation right there. So what do we have? We have -3, weight of BD is given right here. So -3 times 4/12 plus dx times 6/12. I still don't know that, but that's what I'm trying to solve in the first place. Alpha, or I, moments of inertia, that thing is 0.17361 divided by 32.2, and then times 88. Alpha BD is what we solved for, then plus mass 3/32.2 times acceleration of g in the y. That is, what was it? So, does anyone have the acceleration of g in the y direction? Do you have it written down? It's either 10 or 74.3.
74.
74. Okay. Was it positive?
I wrote a, yeah.
Yeah, okay. Cool, then that times 4/12 plus 3/32.2 times -10. That's the acceleration g in the x direction times 3/12. So it's one equation, there's one unknown. You just solve for dx, right? Everything else is just numbers, just computation at that point. I'll put parentheses over things though, just to emphasize things. But as you can see, that's just a number, that's a number, that's a number, that's a number, dx. One equation, one unknown. Dx is equal to 7.1 in the I direction, and this is, we're in English units, so it's pounds. That's the answer. The reaction force at D is 7.1 pounds in the I direction. Yep, that is it. So, any questions? If not, that's it. So, thank you for listening.